Hello everyone, and welcome to my virtual presentation on predictive modeling of periodic behavior for human-robot symbiotic walking at ICRA2020. State-of-the-art prosthetics have come a long way in recent years, and cutting-edge robotic prosthetic ankles are now more robust than ever before. However, modern prosthetics have a major hurdle to overcome in order to produce long-term safe and ergonomic control actions for their human partner. Namely, long-term prosthetics users have a significantly increased risk of developing secondary conditions such as osteoarthritis due to an increased joint load in the knees and hips. Current approaches are unable to address the issue of increased joint forces for a number of reasons. First and foremost, it is challenging to calculate latent biomechanical features such as joint loads in real time. Without real-time estimates of latent variables, the controller will be unable to adapt to the human motions in the most safe and ergonomic fashion. Some systems exist which utilize complex models along with mathematical approaches such as inverse dynamics to solve for biomechanical values. However, these approaches are too computationally complex to run on the low-power hardware that prosthetics require. Additional opportunities to improve on current prosthetics control approaches include adding the ability to anticipate future actions and to produce estimates of how certain the controller is of the current state in action. To these ends, we propose periodic interaction primitives, a data-driven approach to the predictive modeling of periodic behavior for human-robot symbiotic walking. That is, effortless walking with an intelligent prosthesis. Our method takes collected sensor data from human walking demonstrations and, using state-of-the-art biomechanical simulator, augments it with computed biomechanical values such as joint angles, forces, and moments. We then learn a Bayesian framework which generates predictions of the biomechanical state and action of a subject given the requisite observable sensor values. Once trained, a periodic interaction primitive anticipates the future state of the human user from observed sensors and infers the latent unobserved variables such as internal biomechanical variables or device control values without the necessity of further biomechanical simulations. The learning process starts with the concatenation of observed sensor vectors with their associated augmented observations. Now, probabilistically, the objective of periodic interaction primitives is to infer estimates of the future state of the full observation vector given a subset of the observations. We simplify the process by projecting the full trajectories in time into a low-dimensional space using von Mises basis functions to account for the periodic nature of the behaviors we are observing. We can then rewrite our goal equation to incorporate the basis function approximation, and we see that it can easily be solved recursively with a Bayesian filter. In this work, we're utilizing a Kalman filter to achieve human action prediction, latent variable prediction, and robot action generation. It's important to note that by incorporating the basis function decomposition, we now require an accurate phase estimate. In prior work, this was achieved through dynamic time warping, a method which achieves time alignment between two trajectories by finding the path of minimum cost between them. However, we found this method too computationally expensive to run in real time on our device. Instead, we created a novel approach of time aligning our training data in the high dimensional space and then projecting the phase into a 2D lookup table. This method allows for fast and accurate phase estimation of any single observation. We show here an example stride in which each observation is projected into the phase space using the phase manifold. We tested our method on human subjects who generated training demonstrations by walking at different speeds with inertial sensors on both thigh and shank, and instrumented shoes, which sense foot pressure in multiple locations. Motion capture and ground reaction force were additionally used to generate 3D angles, forces, and moments of the ankle, knee, and hip. During inference, our model then uses only the inertial and foot force sensors to generate optimal biomechanical predictions, of which the ankle angle prediction was sent to a robotic prosthetic as the desired position control signal. Periodic interaction primitives displayed significantly lower error in comparison to other Bayesian approaches for both action prediction as well as latent variable prediction. Additionally, we see that since we are using complementary modalities, we see limited degradation in the accuracy when sensor dropout occurs. Even when the observation has been reduced to a single functional sensor, fairly accurate prediction is possible. Likewise, due to its synergistic nature, periodic interaction primitives produces accurate control outputs compared to commercial controllers. Finally, the entire system can run in real time on low-power prosthetic hardware. In summary, we've proposed a data-driven method for the predictive modeling of periodic behavior. Periodic interaction primitives facilitates prediction of human actions while walking, as well as generation of control signals for assistive devices through its integrated phase estimation process. Most notably, this approach extends interaction primitives to latent variables, which are either unobservable or hard to measure in practice. Results in experiments with human participants indicated that periodic interaction primitives efficiently generated predictions and ankle angles, control signals, for a robotic prosthetic ankle, even of subjects that the model was not trained directly on, with a mean error of about 2.2 degrees in only 0.008 of a second. We're currently working on utilizing the Bayesian framework to go a step further and generate optimal control outputs in response to predicted biomechanical variables, effectively nudging the human subject into a more stable, efficient, or ergonomic regime. Thank you to everyone who made this work possible.